In this video, we're computing the geometric area bounded between f of x equals 1 over square root 1 minus x squared, and then g of x equals 1 plus x. So g of x is this simple linear function in the diagram, and f of x is this function with upward curvature. And the reason I said geometric area is to distinguish it from signed area. We're not counting any area as negative here, we just mean ordinary geometric area. So we're going to go through kind of the standard solution to this problem and compute the area bounded between these functions on the interval -1/2 to 1/2. But then I want to get into sort of an advanced symmetry issue that really surprised me in this problem, and it gives us an alternative way of solving it. So we'll go through that symmetry approach to the problem at the end. So to get the area between these two functions, we're going to have to split the integration interval at the intersection of the two functions, and we'll start on the left side. So we visualize a tiny little slice of area. We'd normally call that dA for an infinitesimal slice of area. And because f of x is above g of x on this interval, and we need our height to count as positive because all this area needs to count as positive, we're going to write down the height as f of x minus g of x. And notice I also put the width of that little slice dx into the diagram. So I'm just going to call this left area, I'm going to call it AL, and that's given by the integral from -1/2 to 0 of f of x minus g of x dx. Again, the order of the subtraction there for the height of this little slice was done intentionally to produce a positive result for the area. So we plug in our functions, and we end up with this pretty ugly looking integral of 1 over square root 1 minus x squared minus the quantity 1 plus x on the interval -1/2 to 0. Now, as it turns out, the integral of that square root piece, that's just an inverse sine function. So this is just one of the standard antiderivative formulas that you memorize. So we start out with inverse sine of x, and then we're going to distribute this minus sign and integrate each of those pieces. So that gives us a minus x and -1/2 x squared. And we evaluate this from -1/2 to 0. Now, when we plug in that upper limit, actually every term in this expression vanishes. When I replace x with 0, the two power function terms are going to be 0. It's just -0 and -1/2 times 0. And then the inverse sine of 0, that means the angle whose sine is 0, which is also 0. All right, so everything in the upper limit vanishes. And I subtract what I get by subbing in my lower limit. So I end up with inverse sine of -1/2. What's the angle whose sine is -1/2? That's -pi/6. And then minus a -1/2, which is +1/2. And then I sub in the -1/2 into this quadratic term. And that gives me a 1/4 when I square it. And then multiply that by -1/2, and I get -1/8. So we can go ahead and distribute that minus sign. And we get a left area of pi/6 minus 1/2 plus 1/8. And I'm going to just leave the answer like this instead of simplifying the fractions because we get a really cool cancellation at the end. So now we're going to move on to the right side of this area. So there's a tiny slice of area right there. But this time, g of x is the function that's on top. So if we want our height to be defined as a positive number, we're going to have to put that first in the subtraction. So there's our height, g of x minus f of x, and our little width, dx. So we can write down the area of the right-hand side. This time we're integrating from 0 to 1/2, and we're putting g of x first. So we sub in our functions again. G of x is 1 plus x. F of x again is this ugly square root thing, 1 over square root 1 minus x squared. And we're really guessing all the same antiderivatives. So we're used to the procedure by now. I end up with an x plus 1/2 x squared minus the inverse sine of x. And we're evaluating this from 0 to 1/2. Now this time, when I sub in the lower limit, everything vanishes. Replace x with 0, and the first two terms are gone, and then I have the angle whose sine is 0, which is again 0. So everything vanishes there. That's really nice. And all I have to look at is the upper limit. When I sub in 1/2, I end up with 1/2 plus 1/8, and then minus the angle whose sine is 1/2. Well, that's pi/6. So minus pi/6. All right, so it's time to get the total geometric area bounded by these two functions, and that's the sum of the left and right areas. So that's AL plus AR. And what I notice here is that the vast majority of the terms are going to cancel out. So check this out. The pi/6 plus -pi/6, that's gone. The -1/2, the +1/2, that's gone. And all I have left is a 1/8 plus 1/8. And that gives me 1/4 for the total area. Now, these cancellations surprised me and troubled me because anytime you have a big amount of cancellations happening in a problem, that indicates there must be some kind of underlying geometric symmetry to explain this. But I didn't see it in advance of doing the integrals. So it took a little bit of thinking to see what the symmetry issue actually is in this problem, because we're not dealing with just simple even and odd functions here. So it took a little bit to see what the underlying symmetry was for the problem. And here's how it turned out. If I draw a horizontal cut line through the intersection of these two graphs, I can see that this little chunk of area underneath my 1 over square root 1 minus x squared function is exactly the same as this little chunk of missing area underneath that curve on the right-hand side. So the idea is that we could cut out that little chunk from the left-hand side and then transplant it over on the right-hand side. And now we just have two simple triangles. And then one way to think about it is we could just shift our origin up to the intersection of the two graphs. And really what we're looking at for the area on the right-hand side is the integral from 0 to 1/2 of x. It's just a line with a slope of 1 passing through the origin, dx. So that's the area of the right-hand triangle, and then we can just double that to get the total area. So then I have twice 1/2 x squared evaluated from 0 to 1/2, and our 2's cancel out, and I end up with 1/2 squared, which is 1/4, and the lower limit vanishes. So I was surprised that this symmetry issue popped out of a problem like this. And the natural next question is, under what conditions can you look for symmetries like this to simplify an area problem? So this is one of those problems where I ended up with more questions than answers, which to me is a perfect calculus question. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.